Welcome back to Computer Science Theory. This is COMS W3261, offered Summer B 2021 at Columbia University. And this is lecture, I think it's 5.2, where we're going to introduce context-free grammars. So we've just seen a whole bunch of stuff having to do with the regular languages. So we've seen that DFAs and NFAs and regular expressions all describe regular languages. We've also talked about non-regular languages, how to prove using the pumping lemma that certain languages are not regular. Now we get to go beyond. The idea here is we're going to introduce a new, more powerful way of describing languages. And I've kind of let the cat out of the bag already by telling you that it's more powerful. We'll actually come back to this. First, we're just going to talk about some rules for generating languages, and then eventually we'll show that they're a little bit more powerful than what we've been doing thus far. So here's an example of what a CFG looks like. So we have something to reference. A context-free grammar is going to consist of substitution rules. And they're going to tell you, take a symbol like A and turn it into a 0 followed by a capital A followed by a 1. Or alternatively, take a symbol like A, turn it into the symbol B. Or take the symbol B and turn it into the pound sign, the pound symbol, the number sign, whatever you want to call it. So anytime you see a context-free grammar, it'll come with a set of substitution rules that look like this. And the substitution rules will include variables, which are things that can be substituted. So in this case, our variables are A and B, and then they are often, not always, we'll see a couple of exceptions, but usually for convenience, we'll write our variables as capital letters. And the reason we write them as capital letters is to distinguish them from the symbols that appear as we use these substitution rules that can't be substituted, and the things that'll be left over at the end, which are called terminals, because it's sort of the end of the line. They're terminal symbols because you can't substitute them again. So terminals are symbols in the final string, cannot be substituted. So in this case, our terminals are 0 and 1 and pound. How we generate a string. So if we're looking at this example, maybe you can imagine, but I'll write down the rules formally. So if you're given a set of rules, here's how you can use them to generate a string. We start by writing down the start variable, which is given at the top left. 2, replacing any variable using a substitution rule. And then that's basically it. We just repeat step 2. Repeat step 2 until only terminals remain. So that's how every evaluation, or a production, as it's sometimes called, of a context-free grammar is going to go. It'll always start with one variable at the top left, which we'll call the start variable. And then that variable will proceed to evolve according to substitution rules until we get to a string that only has terminals left. So we can think of a grammar as a guide to producing terminal strings. Like a regular expression, it gives us many ways to produce terminal strings. So a grammar could produce an infinite number of strings depending on how it's defined. If I was going to do an example on this particular grammar up here with 3 substitution rules, I could start by writing down the start variable. That's A, it's in the top left. And then I'd go to step 2. So replace any variable using a substitution rule. Well, in this case, I've only got one variable, A, so I have to replace it. And I actually have 2 substitution rules, right? For A, I can turn A into 0A1, or I can turn A into B. And I can replace this variable using any substitution rule. So whether I choose A or B, or rule 1 or rule 2, will determine what my final string is. Certainly, this is how we get all these different strings. But I can choose either one. They'll just make different derivations. So maybe I'll use the first rule. I'll replace A with 0A1. Now I have a new string, so I go back and I replace another variable using a substitution rule. I've got another A. I could use the same rule again if I wanted to. I could go from A. Maybe I'll do that. I'll go from A and replace A with 0A1. So I've still got my first 0, and I've still got my last 1. These 0s and 1s remain unchanged, but I substitute in my A for another 0A1. Now maybe I'll choose to use my second substitution rule. I've still got variables left, so I keep doing step 2, replacing any variable using a substitution rule. I'll replace my A with a B this time. Now I've got 0, 0, B1, 1. B is still a variable, so I'll do step 2 one last time, replace any variable using a substitution rule. So I'll substitute B for the pound sign and wind up with the string 0, 0, pound 1, 1. And at this point, only terminals remain. So every symbol in my derived or produced string is a 0, a 1, or a pound. And that represents a complete derivation. So I've started at my start symbol, I followed some sequence of rules, and I've ended up with a certain string. Maybe you can tell that if I followed a different sequence of rules, I would end up with a different string. And we can think of a grammar as an object that produces a bunch of strings according to these rules. So we've seen this word grammar before, at least I've mentioned it. Grammar is a word that you might see and immediately think language, and you would be right to think that. Grammars in precisely this sense have a long history in the field of linguistics. So, for example, a dude called Noam Chomsky, who is a social critic and a professor and very old, still banging around, still producing provocative theories. Among other things, he popularized the idea of a universal grammar. This is the idea that humans have a schematic grammar, kind of like this one that I've drawn on the page, embedded in our brains. And all of the human languages are variants on this grammar. We set a few parameters, and after we set those parameters, we end up with an implicit grammar that determines what strings, what sentences are well formed in our language. And this theory is still somewhat controversial, but it seems to describe almost all languages very well. And if you've parsed sentences before, if you've written down English sentences and divided a sentence into a noun phrase and a verb phrase into a verb and an object and indirect object, you've done this process of replacement before. You've started with a start symbol, a sentence token, and you've generated words. You've gone through intermediate variable symbols, like noun phrases and verb phrases and stand-ins for nouns and adjectives and prepositions. And you've eventually plugged in words in the language you're interested in studying. So universal grammar, I guess one way you could state that thesis is the thesis that there is a generative grammar like this one, like this context-free grammar for every language. And that grammar is a great way to represent which strings, which sentences are well-defined, and even think structurally about their meaning. In computer science, we'll use that sort of linguistics a lot to take apart sentences in the field of natural language processing. So that's my grammar tangent number one. A second grammar tangent is there's a connection between grammars and programming languages, which I think a couple of you have asked me about in office hours. Oftentimes, when you write a compiler for a programming language, what does a compiler do? It reads in your program, it figures out what the program means, and it converts it into simpler code, often machine code, that then goes to the processor and lets the processor run your program. And to do that, usually the compiler needs to start with what's called a parser, something that reads through your code and breaks it up into pieces. And the parser is often based on a context-free grammar for the programming language. This may be a strange way to think about programming languages, but if you've ever programmed in a language, I don't know, like C, for example, you can start with a start state, which we'll just say is like represents any program that evaluates to any object. And we can say, well, okay, a program can be a truth value, it can be a data value, or it can be some more complicated string of things that produces a truth value or a data value that can have intermediate operations like loops, like references and jumps. So believe it or not, there are often context-free grammars for programming languages. So those are my two tangents. Context-free grammars in general, are powerful formal tools that are used in linguistics, in natural language processing, and in programming languages. So not just math objects. Well, yes, just math objects, but useful ones. And ones that I hope you think are cool. All right. I'm going to do another couple of examples just so we have them for reference. If I'm looking at my grammar that takes an A to 0A1, an A to a B to a pound sign, I could certainly derive different strings. So I could start with an A, and then in step 2, replacing any variable using a substitution rule, I could just substitute B for A. And then my only rule for B is pound sign. So I'd get pound sign. This is a string of only terminals, and this is a complete derivation in the language. Pound sign is in the language. Or I could go A to 0A1 to B, substitute my A for a B, maintaining my terminals on either side, and get 0 pound sign 1. So these are all examples of valid derivations. I'll define that formally. So a sequence of substitutions used to create a string of terminals is called a derivation. So these 3 things above are derivations. They start with a start variable. They end up with a string that is produced or derived, and the entire sequence, which follows production rule after production rule after production rule, is a derivation. You could also write these out in English if you wanted to. Like you could write a sentence. I'm going to use rule number 1 to substitute the start variable a with 0a1. Then I'm going to use rule number 1 to substitute the symbol a with 0a1 to get 00a11, and so on. The arrows is just an abbreviated way of writing down the derivation. And there's one other important way of representing a derivation pictorially that again might ring the I've done this in English class bell. We can represent a derivation pictorially with a parse tree. So this is another handy visual way to show how we derive a certain string from a certain grammar. Like for instance, parse tree for say 00 pound 11, which hopefully you believe is in the language. Yeah, we showed that it was in the language. How we draw a parse tree is we start with the root, and then we draw our replacements as a step down on the parse tree. So instead of writing a arrow 0a1, I'm going to make 0, a, and 1. I'm going to write them out as nodes descending from a. And you can see how, even if I had more than one variable, I could just continue this process and end up with something that looks like a tree. So my second substitution, we look up, we're just going to track this derivation up here. I'm going to substitute my a for 0a1 again. 0a1. And then I'll substitute a with a b. And finally, I'll substitute b with a pound sign. So what I'm doing here, substituting each symbol according to the rule we use as we move downward. We read a parse tree by concatenating symbols left to right. So by that, I just mean if you saw this picture and you were wondering, okay, what string does this represent? I would start at the far left, read a 0, read a 0, read a pound sign, read a pound sign, and read a 1. So I'm just reading all of the terminal things. So terminals being leaves in this parse tree. Every variable will have descendants because it'll be substituted. Every terminal will be a leaf of the tree. And I get the string 00 pound 11. This also tells you that the order in which you write the symbols in a parse tree is important. So, for example, for the substitution a to 0a1, I would want to write it 0a1, and that would be different from writing, I don't know, a1, 0. So in a normal graph, these are all just nodes that are connected to or descended from A. But in a parse tree, the order I write from left to right is going to matter because that indicates the order in the string. So hopefully that's clear. We'll just start with A. We apply a rule and write down all the symbols that descend from A below it. At this point, if you're thinking about languages, your brain is in the right ballpark. There is a natural language connected to every grammar. For this one, you may have observed it already. So we'll say the language L, G, the grammar G is the set of all strings that can be produced by derivation. So in this particular case, where I'm writing my grammar this way, A to 0, A1, A to B, and B to pound. And I'm going to call this grammar G. Then we have that the language of G is just 0 to the n, pound, 1 to the n, such that n is greater than or equal to 0. So no matter what, based on this production rule, I'm going to have the same number of zeros and ones, because the number of zeros and ones I end up with is the same as the number of times I used rule 1. Similarly, I'm never going to run out of variables until I go from A to B and from B to pound. So there's always going to be a pound sign in the middle of my string. So hopefully you can see that this grammar generates all strings that have the form 0 to the n, pound, 1 to the n, for some n greater than or equal to 0. And when we introduce a new tool that defines a language, there's also a natural class of languages that goes along with that. So when we introduced DFAs, we said the set of all languages recognized by a DFA is the regular languages. We'll do the same thing here, and we'll say the set of all languages produced by a context-free grammar is called the context-free languages. So we'll abbreviate context-free grammar often as CFG, and the context-free languages as the CFLs. Not GFG, CFG. So we've got context-free grammars, and we've got context-free languages. Let me do a linguistic example for you. Give you a little bit more of a context-free grammar to chew on. Here's another example of a context-free grammar. And this one is an English fragment. So my rule number 1, I'll let S be a start symbol, and I'll say you can replace S with NP, VP. And in this particular case, usually our variables will be one single capital letter. But in this case, I'm using these angle brackets to denote one single variable symbol. So NP and VP, we're thinking of them as one symbol, and the angle brackets are denoting that. Let's say you can turn an NP into a variable A, concatenated with a variable N, a VP into a V, an N into the terminal symbols DOG or CAT or CAR, or SHOE or person. You can turn the variable v into smells or sees or is or eats. And you can turn a into, how about a or the. So this is a grammar just like the one above. This grammar has a whole bunch of rules. And in particular, I've introduced another little piece of notation. So I'll say the bar, that's this straight line symbol. What did I do there? Abbreviates multiple rules as one. So the bar is not a scary operation. It's just letting me write, the rule n to dog and the rule n to cat and the rule n to other stuff. It's letting me combine a whole bunch of rules into one line. So this is just an abbreviation. It's just a way of writing down a bunch of rules without having to rewrite n arrow a whole bunch of times. It's saying I can turn n into any one of these 5 things, and I have a rule for each. So 6-rule context-free grammar. And just as before, we can follow our 3 rules to start with our start symbol and derive strings in the language of the grammar, the context-free language that the grammar recognizes. So I'll start with S. There's only one rule for S. So from S, I'll substitute. We go to NP-VP. Now for the first time, we have 2 variables in our evolving string. And if you look up at rule 2 above, you'll see that I can substitute either variable at this point. It doesn't matter which. I can substitute NP or I can substitute VP. And I can also use any of the rules associated with these 2 things. In this case, it doesn't matter too much because there's only one rule for each. So I'll substitute NP for AN. I'll keep VP. And then I'll substitute A for capital A for lowercase a. So my string now has 1 terminal and 2 variables. Terminal is A, the variables are N and VP. Maybe now I'll substitute VP. So I'll substitute VP for V, A, N, V. I'll substitute N for shoe, A, shoe. I'm adding a space here to make it legible, although I haven't really made that clear in my grammar. If this was a strict string, there would be no spaces. It would just be strings of characters. I'd have to add a little bit more complexity to make these spaces a formal part of the grammar. I've still got my verb symbol. And then maybe, let's get existential. Switch V for is. A shoe is. Period is not part of this string. Neither are the spaces. The shoe exists. If I want to get more complicated with my grammar, I can I can add more rules, add more possibilities. So, I can add a rule that lets me turn a verb phrase, a VP, into a verb concatenated with a noun phrase. So I could do another derivation where I go from S to NP-VP to NP, and then I'll substitute VP for VNP. So now I have an NP concatenated with V, concatenated with an NP. And if I keep deriving, That'll use my rule to go NP to AN. I'll go NP to AN again. ANV AN. And then after 5 more steps of substituting these symbols for strings of terminal symbols in my alphabet, this is just the Roman alphabet, A through Z, is one way to think about the alphabet this grammar is using. We'll get, I don't know, the cat sees the person. I've skipped 5 steps. Each of these steps will replace one of my variables with a terminal. So this is a very basic version of English grammar. If you wrote out a grammar for English, it would look a lot like this. It'd be a little bit more complicated, and you would have some people looking at you like, hey, you know, you've imposed a formal construction from the top down on English. English is not prescriptive. It doesn't follow from rules. It's descriptive. It's a thing in the world that people speak, that we go out and look at. And those people are all right up to a certain point. Grammars are formal objects that we make because we're formal scientists. And if they fail to describe the world, that's on us. But they also have nice properties that we can prove things about. So we can say very precise things about our formal language that we can't necessarily say about the observed phenomena of English in the real world. So pros and cons, and fun linguistics tie-ins. So we've done a couple more derivations of this simple English context-free grammar. I want to do a backwards example, although it'll be a little harder. Like suppose I gave you the string, the dog eats a shoe, and I asked you to figure out, is this a string in the language of this grammar? One way you could prove that this string was in the grammar would be by reasoning backwards and converting terminal symbols into variables. Now, unlike our first process, turning variables into terminal symbols, which is completely well-defined, we just iteratively replace any variable according to any substitution rule. Going backwards is more of an art. Sometimes there are multiple ways to derive the same string, and sometimes the ways of splitting up terminal symbols and transforming them back into the variables that produce them are ambiguous. Like, you know, if SAS was a word produced by some terminal symbol, we could go down the path of saying, well, SAS must have come from this other variable, and do a back derivation that did not come out correctly. It didn't get us back to the start symbol. But in this particular case, you'd probably be able to look at this and say, well, okay, that's pretty clearly, you know, one unit, and it must have been produced by this variable A. And, you know, dog probably came from N, eats probably came from V, A probably came from capital A, shoe probably came from N. Then, you know, oh, there's an AN, well, that probably came from NP. This AN probably came from NP. Oh, there's a VNP chunk. Well, VNP, that sounds like a VP. And then finally, we've got NPVP. That probably came from a start symbol. So again, there could have been, you know, there could be multiple ways to derive a string. So this back derivation might not be unique, and it might not be always as easy as it is in this case. But, you know, often in practice, you can go backwards as well as forwards. Forwards is easy and procedural. Backwards could require some creativity. All right. Now, for the tuple fans in the audience, the people who see a picture of a DFA and immediately start writing parentheses and drawing in 5 objects, I've got a formal definition of a CFG that will make the things we've been talking about precise mathematically. So this is the formal definition of a CFG, a context-free grammar. A context-free grammar is a four-tuple Our four-tuple will be V, sigma, R, and S, where V is a finite set called the variables. So to formally define my grammar, I've certainly got to tell you what the variables are. Sigma, as you might expect, is a finite set, not usually called the alphabet, because there's also variables that we see sometimes. It's a finite set called the terminals. So we've got our variables and our terminals. Our terminals have to be disjoint from V. What disjoint means is that they have no elements in common. So in particular, it would be a confusing thing if I had a symbol that was both a variable and a terminal. I wouldn't know what to do with that. So we just specify in our definition that V and sigma don't have any elements in common. They're two disjoint sets. R is a finite set of rules. So these are the production rules we've been writing down to substitute variables for strings of variables and terminals, where each rule maps one variable to a sequence of variables and terminals. For example, A, right arrow, 0, 1, A is a perfectly good rule. It says we can take the variable A, so we're mapping one variable, and we can replace it with a sequence of variables and terminals. The terminal 0, the terminal 1, and the variable A. And then finally, S, which has to be a member of our variable set, is the start variable. We have to know where to start. We have to know what variable is in our string at the beginning that we generate the rest of our string from. So this is the entire definition of the CFG. We'll add to the formal definition some instructions for how they work. So we'll say for any strings of variables and terminals, U, B, and W, if there's some rule, A, right arrow, W, I'll say if A, right arrow, W is a rule of the grammar, then we say that U, A, V yields U, W, V, where yields is written UAV, arrow with two bars in it, UVW. This is just a formal way of saying if I have any strings U and V on either side of A. So some stuff could be the empty string, then the variable A, then some other stuff could be the empty string. U and V can include some variables and some terminals or anything else. The rule A to W lets me turn that string U concatenated with A, concatenated with that string V, into the string U concatenated with the string V, W concatenated with the string V. Substitution. And we just say UAV yields UVW. So it's a formal wordy way of saying you can substitute A for W. Similarly, for any strings of variables and terminals, U and V, we say U derives V, which is written U, arrow with 2 bars, star over the arrow, V. If U equals V, that's the really basic case. If U and V are the same, U derives V. Or if there exists a sequence U1, U2, ... UK for k greater than or equal to 0, such that U, after using some rule, yields the string U1, which after using some rule yields the string U2, ... which eventually yields UK, which eventually yields V. So what we've just done is we've defined this double arrow to mean yields, which means you can get from one string to another string using a substitution rule. And then we've defined the term derivation formally for our context-free grammar. We've said U derives V if there's some sequence of rules that takes us from U to V. We can also redefine the language of a grammar formally. So we'll say the language of a grammar G is any string over the alphabet such that starting from the start symbol, you can derive W. And if you look back up at our informal definition of the language of a grammar, you'll see that this exactly matches up with it. So the language of a grammar G is all the strings you can make, all the strings that you can derive from the start string. S derives W, well then S is in the language of our grammar. Cool. This is our formal definition of a grammar. It works just like the informal grammars that we've been writing down. As an example, we can certainly, previously we've just been writing down the sets of rules, right? When we wrote that grammar with A and B, we just wrote down a set of rules. And usually that's really all you need to define a grammar, right? We've written down the set of rules. The alphabet is kind of implicit, and the variables are implicit in the rules, and the start variable is just the variable on the top left. But if we wanted to do it formally, we could say, we could define some grammar G4. The only reason I'm calling it G4 is because it's called G4 in the book. I want to make it easier for you guys to look back and find it. And we'll define it to be the set of variables V, the set of terminals sigma, the set of rules R, and the specific variable expr, where the set of variables is expr, term, factor. Again, I'm using angle brackets to say that these are all, you treat them as one symbol, treat each one as one specific variable, even though it's not a capital letter. The set of terminals is going to be the letter A plus times left parenthesis, right parenthesis. Because I know it was a little confusing on the homework. For this question, just to be perfectly clear, this is the times symbol. This is the symbol you see in grade school when you write A times B. It's not the letter X for this particular problem. Then the rule set is just this set of rules. I can take an expert or an expression, and I can turn it into an expression plus a term, or just a term. Remember that my bar denotes or, so I've written two rules in one here. You can either take an expert, turn it into an expression plus term, or you can use the second rule that takes an expression and turns it into a term directly. A term can be a term times a factor, or just a factor. And finally, a factor can be an expression with parentheses on both sides. Parentheses in this case are terminal symbols, or the letter A. So this is a grammar formally defined. If I just gave you the rule set, that would be me defining it a little bit less formally. You could read the rule set and say, okay, I'm interpreting the start symbol to be the top left symbol, that's expr. I'll interpret the set of variables to be expr, term, and factor. Those are all the things that start substitution rules. And then the terminal symbols are everything else I might see in my string. So I might see a plus sign, I might see a times sign, I might see open and close parentheses, and I might see the letter A. And of course, you can just use this grammar as we've been using it. Like if you wanted to derive A plus A times A, let's do it with a parse tree so we can see parse trees one more time. I'll start with my start variable expr. I'll use a substitution rule to turn expr into a term. I will then generate my times symbol by turning a term into a term times a factor. And I'm just following my two-step process here. I already know the string I want to get, and I already know how to get there. So it's going fast. But all I'm doing is saying, I've got a string, it just has term in it. I'm going to use any of the rules that starts with term to turn term into something else, term x factor. From factor, I'll put in the A that's at the end of my string. And from term, well, I'll go to factor. And from factor, I'll go to parentheses around a new expression. Now maybe you can start to see my final string taking shape. I've got a parentheses thing, I've got a times A, and then from expr, I want to get to expression plus term. Term goes to factor, goes to A, expression goes to term, goes to factor, goes to A. So big old parse tree for a not too complicated expression. And if I was to read this off of my parse tree, I would see left parenthesis, then an A, then a plus, then an A, then a right parenthesis, then a times, then an A. So that is left parenthesis plus A, right parenthesis, times symbol, A. Cool. I have done the forbidden, I've crossed the line. you should be able to see, at the very least, you should be able to see when you're looking at these notes, the entire parse tree above the line. I've shown you a bunch of CFGs. Next, I want to talk a little bit about building CFGs. So we haven't given you any formal procedures for going from a CFG to the language it represents, besides testing a bunch of strings. And unfortunately, I can't give you a formal procedure for going from a language to a CFG. But I can definitely introduce a couple of tricks that'll help us think about it. The first trick is, suppose we want to build a CFG for the language 0 to the n, 1 to the n, such that n is greater than or equal to 0. Union 1 to the n, 0 to the n, such that n is greater than or equal to 0. So this is one single language, but it's the union of two other languages, two other non-regular languages. So it's all the strings that are zeros and ones, sorry, a substring of zeros followed by a substring of ones, and those two substrings have the same length, and vice versa, a substring of ones followed by a substring of zeros, and those two strings have the same length. There's a technique which is easy to use if you want to build a CFG for a union, and that's building a CFG for the two separate languages and then combining them together with the new start symbol. So in particular, I claim that the language S1 to 0 S1 1 for the empty string. I claim that this recognizes 0 to the n, 1 to the n, such that n is greater than or equal to 0. And to see this, you can observe, and by the way, this is a complete grammar. It's got two rules, abbreviated, written as one rule. I start with the start symbol S1. I can then replace it with 0, S1, 1. I can keep doing that an arbitrary number of times. That's going to generate some zeros on the left and some ones on the right. It's going to generate the same number of zeros and ones. If I use the rule 6 times, it's going to generate 6 zeros and 6 ones. And then at some point, the string I generate, the string I derive, will end when I substitute S1 with the empty string. So I claim that this recognizes the language 0 to the 1, n to the 1 with n greater than or equal to 0. And very similarly, I can do another language, just the reverse. That'll recognize the second language in my union. The symbol is supposed to be an S. So now I have CFGs. This is two separate CFGs that recognize the two separate components of my language. To take the union of these CFGs, add a new start symbol. So now essentially what I've done is I've added a new rule. I've said the new start symbol is S, and from S you could either S1 or S2. And you can kind of see why it's a union gadget, right? No matter how I derive a string in this new grammar, that string is going to start with an S, And that S is going to turn into either S1 or into S2. If I take the first choice, I end up with just an S1 and I produce a string in the first language. If I take the second choice, I end up with just an S2 and I produce a string in the second language. So clearly, the set of strings that this grammar generates is going to be the union of these two languages. If I say that this is the language L, then the language of G is L. That's the first little technique. Second little technique, these languages were not regular. We built a CFG for them. So actually, let's do a little aside. We made a CFG for a non-regular language. So maybe the context-free languages is a bigger class. Foreshadowing. Here's another technique. Converting a DFA to a context-free grammar. So, you know, suppose we have the language L is W, such that W is in 0, 1 star. So it's some string over the binary alphabet. And W has an even number of ones. So say we've got this language, and suppose you're staring at it and you're not sure how to make a CFG, but you think maybe you can figure out how to make a DFA. So in particular, I believe that's a DFA because it has outgoing edges on 0 and 1 from every state. And I think it should recognize all the strings that have an even number of ones. The logic there is that this DFA accepts the empty string that has 0 ones. It'll accept all the strings of only zeros. They have 0 ones. And then effectively, I'm either in state Q1 if I've just read a 1 and I now have only read an odd number of ones, or I take a 1 back. Whenever I'm in Q0, I've read some even number of ones. So I'll accept if I reach the end of my string after reading an even number of ones and reject otherwise. I claim we can convert this DFA to a context-free grammar as follows. One, we make a variable Ri for each state Qi of the DFA. So we'll have a variable R0 and a variable R1, right? One for each state in our DFA. 2, for each transition, delta Qi A to Qj, add the rule Ri to Arj. So now I'm going to add a bunch of rules. So my rule set, well, I'm going to look at every transition in my DFA, And for every transition in my DFA, I'm going to create a new rule in my context-free grammar. So for instance, I have a transition from Q0 to Q0 on 0. So, if I'm thinking about delta Q0, 0 yields 0, strictly speaking, this should be an equal sign, I think. Then in my DFA, I'll create a new rule that goes from R0 to AR0. Likewise, I'll have a rule that goes from R0, not A, 0 R0. I'll have a rule that goes from R0 to 1 R1. That's for the transition from Q0 to Q1 on 1. R1 to 0 R1, and R1 to 1 R0. And if you stare at these rules, you can kind of see why they're going to emulate the DFA. So at any point in this grammar, I'm going to have exactly one variable active. Maybe it's R0. And that represents a state I'm in at an intermediate point of the computation of my DFA. So if I've got some string and one variable, R0, at the end of my string, I'll think of that as, okay, I'm simulating a DFA, and I'm at the point R0. Then, on a 0 or on a 1, I'll write down a 0 or a 1. I'll take one of these first two rules here to indicate that I've read in that symbol. Writing it down in my CFG is like reading it in my DFA. And I'll switch variables to indicate the new state that I'm in. From that new state, maybe it's R1, I can then read in a new symbol, 0 or a 1, and end up in a new state. So I claim that with these rules, I end up writing down a string I might be reading into my DFA while maintaining the current state I'm in as a variable in my CFG. We'll add RI to empty string for each except state. So effectively, that's going to say I might stop reading symbols in an except state. So R0, go empty string. And then finally, I'll say R0 is the start symbol, because it corresponds with R0 is the start symbol. It corresponds with the start state of my DFA. And I guess my alphabet is implicitly the same. That is, my alphabet for the DFA sigma is my set of terminals for the new CFG. All right, sigma equals sigma, and the start symbol is R0. I want to do a quick example just to hopefully convince you that these two constructions are the same. This DFA state diagram accepts or recognizes the exact same language of strings as can be derived using my new CFG. Like, for example, I don't know, 0101 is a string that contains an even number of ones. So it will be in my language. On my DFA, I start in Q0 and compute, well, let's see, I read into 0. So I compute to Q0. That's the first transition. Then Q1 when I read into 1. Then I stay in Q1 when I read into 0. And then finally, I go back to Q0 when I read in my last 1. And then accept. And I claim if we do a derivation in my CFG, where I use the substitution rules corresponding to the edges, I'll generate this same string. So in my DFA, well, I've got to start with my start symbol R0. Then if I want to match the string 0, 1, 0, 1, I'll use the rule that corresponds to going from Q0 to Q0. That is this rule, R0 to 0, R0. And then I want to generate a 1, so I'll use the rule that corresponds to reading in a 1 at R0. So I'll substitute my R0 with 1 R1. So now I have 0, 1, R1. And I'll continue in this fashion. Okay, I'm in R1, I want to read into 0. So I'll use this rule to get 0, 1, 0, R0. Sorry, R1. I'll read in my final 1. So now I have 0, 1, 0, 1, R0. I'm using that rule. And then finally, I will end my string. I'll use my R0 to epsilon rule and get the string 0, 1, 0, 1. So that's an example. I have not formally proved this, but I claim that this informal construction that I have not formally proved works yet. This non-rigorous construction shows that any regular language derives from some CFG. And implicitly, that's because if we have some regular language, then we know by definition we can write down a DFA for it. And we've just shown how to take a DFA and turn it into a CFG. So this means that the regular languages are a subset of the context-free languages. Moreover, we know we can write context-free languages. We know we can write context-free grammars for languages we know are non-regular, right? We know this language. We know this language is non-regular, but I claim we can easily write down a context-free grammar for it, just the context-free grammar that spits out an even number of zeros and ones. So context-free languages are not a subset of the regular languages because there are context-free languages that are not regular. So with this, just with our building techniques, we've managed to build a bigger picture of the universe. Regular languages inside this larger class of CFLs, and that's pretty cool. All right. Yeah, I want to go over one more concept and then we'll wrap for the day. So one last concept to know about context-free grammars. We mentioned earlier that sometimes you can generate the same string multiple ways. I want to show you a quick example of that. So I'll say if a grammar generates the same language in more than one way. Actually, I want to be more specific about this. If a grammar generates the same language in ways corresponding to different parse trees, it is ambiguous. So why I've specifically used the words different parse trees is to account for this rule where we're allowed to replace any variable. So, if I have this grammar, you can derive the string 1, 1 by going S to AA to 1A to 1, 1, or by going S to AA to A1 to 1. In other words, I've just changed which variable I'm substituting. So I can either change my first A to a 1 first or my second A to a 1 first. But that's not really ambiguous. Like, in a way, I've just done the same two rules that were going to inevitably happen anyway in a different order. So I do want to distinguish from that. I'll show you an example of a language that's truly ambiguous. So consider the grammar G5. It's a 4-tuple consisting of B, sigma, R, and say the start symbol is E, where the only variable is capital E. The set of terminals is going to be plus symbol, times symbol, left and right parentheses, and A. So we're dealing with another mathematical grammar here. And the set of rules is as follows. E can turn into E times E, or E plus E, or parentheses around E, or finally the terminal symbol A. So we'll start with E. We'll think of E like an expression. We'll say an expression can be an expression times an expression, or an expression plus an expression, or parentheses. And now I claim this grammar is ambiguous because there's multiple parse trees that let us get to this expression, or also actually to many expressions. This is just one example. To show that a grammar is ambiguous, all you need is to show is some string that can be generated in multiple ways. And in fact, I'm going to write this definition in terms of strings just because I think it's easier to digest. It's the same thing either way, whether it generates, it generates exactly one language. So generating the same language in ways corresponding to different parse trees just means there's at least one string in the language generated in two different ways. And I claim I can derive A plus A times A by doing a plus first, then doing a times. That's one parse tree. If you read it, you get A plus A times A. But I can also do it by doing a times first. So these two parse trees are substantially different because our left-right order matters. So I have first used EXE rule, and then I've used the E plus E rule on the right. On the left, I've first used the E plus E rule, and then I've used the E times E rule. So that's just ambiguity. Many grammars will be ambiguous. And that's a lead into next time where we'll talk about ways of making sure our grammars are not ambiguous and resolving ambiguities in grammar. One way to do this is with the following definition. We say a leftmost derivation is one in which we always replace the leftmost variable. Formally, a string is ambiguous if, a grammar is ambiguous if it generates a string with at least two different leftmost derivations. So in this particular case, we have e to e plus e, and then the leftmost derivation requirement is going to tell me if that I'm writing down a leftmost derivation, I always swap the left symbol first. It'll just give me a specific way to evaluate. It doesn't change the strings I can make, it just limits the ambiguity as follows. So I'll change my E into an A first. So this is one leftmost derivation. I could also use a non-leftmost derivation. So if I used a rule to replace this right-hand E first, made it E plus E times E, and then completed the derivation. This particular step, where I've replaced a variable that's not to the left, means this is not a separate leftmost derivation. However, this string is ambiguously derived because there is indeed a second derivation corresponding to my second parse tree that is also leftmost. That's where I go E to E times E and continue doing a leftmost derivation. So I'll take my first E, turn it into E plus E times E, and then continue replacing symbols from the left, replacing variables with terminals. So I've written down 3 different derivations for the string A plus A times A. All 3 derivations are totally valid. These are all good derivations, unless I've made a typo. One of the derivations is not a leftmost derivation. So if you see, these first 2 derivations, they don't prove by themselves that the language is ambiguous, because really, kind of the same thing is going on here. I'm just doing my rules in a different order. I'm not going to generate a different parse tree. So both of these derivations correspond to the first parse tree, the parse tree on the left, because I do the plus operation before I do the times. However, there is another leftmost derivation, leftmost number 2, where I begin with the times operation and then go to the plus operation. We will call the language ambiguous because it has two leftmost derivations corresponding to two parse trees. So if the several derivations is confusing to you, it can be helpful to go back and use the parse tree definition of ambiguity to think about it. So that is all for today. Next time, we'll discuss normal forms for grammars and a new type of automaton called a pushdown automaton. As a reminder, homework 3 is due Monday at 11:59 Eastern. And in review, all of this context-free grammar stuff is in CFGs section 2.1. So thanks very much for watching. Have a great weekend. Bye.